We can see the numerical example of Mudmat settlement calculation. Let's go through a simplified calculation for Mudmat settlement using the provided formula and inputs. Mudmat A. Area is considered 50 meters squared. Maximum vertical load Q is 800 kilonewton. Poisson ratio 0.3. Elastic modulus of soil, yes, and shear modulus of soil we need to calculate, and equivalent radius, so equivalent circular footing radius to be calculated, Mudmat settlement also to be calculated. First step is calculate the equivalent circular footing radius. From the A of Mudmat we can calculate the equivalent radius using the formula R equal to square root of A by pi. Substituting A equal to 50 square, R equal to that 3.99 meter. Calculate the elastic shear modulus. We can calculate the elastic shear modulus, the relation between ES and Poisson ratio and G. We could calculate the shear modulus. Elastic shear modulus is 38,462 kPa. Calculate the settlement. Once we plug in all these values in this settlement UV, we can get this displacement as 912 mm or 0.912 meter. In this example, we calculate the settlement of Mudmat under given conditions is approximately 0.912 meters. The settlement value have determined whether the foundation design will be suitable or if adjustments are needed, like increasing the Mudmat area or reinforcing the edges, modifying the materials. Let's have a group discussion on the Mudmat settlement calculations. In this discussion, we will explore the methodology for calculating the settlement of Mudmat, and which is a type of foundation commonly used for heavy structures like offshore platforms of large industrial plants. The key parameters involved in the calculation include Mudmat area, maximum vertical load, Poisson ratio, elastic modulus, elastic shear modulus. The goal is to understand how these parameters influence the Mudmat settlement under the applied load. Mudmat area. Area of Mudmat is a crucial factor because it determines the distribution of applied load over the soil. A larger area typically leads to less settlement, and the load is spread over wider surface. Mat foundations are often designed with a sufficient area to minimize the settlement under a given load. If we have a sufficient area, we can minimize the settlement under a given load. Discussion points. What size Mudmat would be the most effective in reducing the settlement for a given load? So this is a point we need to discuss, like what's the size of the Mudmat, what size Mudmat would be the most effective in reducing the settlement for a given load, and how does the area affect the load distribution in both clay and sandy soils. So how does this Mudmat area affect the settlement or load distribution in both clay soil as well as sandy soils? On bottom load. This is the maximum vertical load applied on the Mudmat. The magnitude Q is determined by the structure's weight and as well as any additional loads like it may carry, and larger Q results in more settlement unless compensated by a larger Mudmat area. If the Q is larger, it could create a larger settlement, and if it is compensated by a larger Mudmat area, we can manage the settlement, we can reduce it. How does the type of load, the example dynamic versus static, affect Mudmat settlement, and would the increasing Mudmat area would always be cost-effective solution to mitigate the settlement? The next one is Poisson ratio. Is a material property that measures the ratio of lateral strain to axial strain in a material subject to axial stress. In the context of soil mechanics, Poisson ratio reflects how the soil will deform under the applied load. A typical value for soil varies between 0.2 to 0.5 and influences soil elastic behavior. How does the Poisson ratio affect the settlement calculation? So we have to understand, like, how does the Poisson ratio affect the Mudmat settlement effect calculation? What happens if the Poisson ratio value is incorrectly estimated? Would higher Poisson ratio lead to more or less settlement? These things we can discuss. And elastic modulus. Elastic modulus of soil measures the soil stiffness. It's essentially understanding how the soil deforms under load. The higher the elastic modulus, less the soil will deform. So if you understand, like if it has the higher elastic modulus, the soil will deform less only. ES is typically measured in megapascals. How do we determine the value of ES in different types of soils, and how does the elastic modulus affect the overall settlement Mudmat, and can the elastic modulus of soil vary significantly across a site? How should we account for that variability? And elastic modulus and shear modulus. Elastic shear modulus and its relationship to the ES. Shear modulus represents the soil resistance to shearing deformation, and it is derived from the elastic modulus and Poisson ratio. So it's a resistance to shearing deformation. How does the shear modulus impact the settlement compared to the elastic modulus, and how can we determine the shear modulus in practice for Mudmat design? An equivalent circular footing radius. The equivalent circular footing radius is determined from the area of the Mudmat using the formula R equal to square root of area by pi. This radius is used in settlement calculation to represent the equivalent radius of circular footing with the same area as Mudmat. The size R affects the distribution of stress and resulting settlement. Of course, the size R affects the distribution, stress distribution and resulting settlement also. How does the equivalent radius help in simplifying the complex geometry of Mudmat? What challenges might arise in applying the circular approximation to non-circular Mudmats? What challenges might arise in applying the circular approximation to non-circular Mudmats? And Mudmat settlement. The settlement of the Mudmat is vertical displacement due to the applied load. The formula to calculate the Mudmat is UV, that point we can see it. And how do we interpret the formula in terms of soil behavior and load distribution? What does each term represent in settlement equation? So we have to see term by term, like what does each term represent the settlement equation? How do changes in one affect the others? If you change one particular parameter, how is it going to affect the settlement? How is it going to affect the other parameters? That's what we have to discuss. And how would the settlement change if the Poisson ratio or the shear modulus increases or decreases? Impact of soil type. Soil type like clay, silt, sand heavily influences the elastic modulus and shear modulus Poisson ratio. It's crucial to accurately determine these properties to ensure the reliability of the settlement prediction. If you want to have a reliable settlement prediction, the measurement of these properties, that's very important. We need to accurately determine these soil properties, because that heavily influences, and soil type also heavily influences these properties, and these properties influence the settlement prediction. Load constraints. It's essential to consider load type and ensure that the Mudmat is sized adequately to prevent excessive settlement that could lead to structural damage. If there is an excessive settlement, that could lead to structural damage. Optimization Mudmat design. To minimize the settlement must be balanced. The settlement must balance the Mudmat area, the load, and the elastic soil properties. We can have one imagine the discussion with the professor. All right, we have got a critical task at our hands. This offshore project is pushing us to the limits of Mudmat design capabilities. The settlement prediction is vital. Do you all understand the variables involved? The question is asked by the professor is that, do you all understand the variables involved? What are the variables involved in this one? And do you all understand all the variables involved in that one, right? Pointing to the whiteboard, I have gone through the calculations, professor. The Mudmat area is given, and we have the applied vertical load, and which is our maximum load, and from there we will compute the settlement UV. But it's the elastic properties of the soil that seem tricky. The elastic properties of the soil, that's very important, and that seems tricky. Like a shear modulus G is linked directly to the elastic modulus. Shear modulus is directly linked to the elastic modulus and Poisson ratio, and that's where the uncertainty lies. Crossing his arms, yeah, but what about the real world conditions? What if the soil's characteristics are not uniform across the site? So what about the real world conditions? What if the soil's characteristics aren't uniform across the site? We are dealing with highly variable conditions out there. The equations are fine in theory, but on the field, it's a different ball game. Professor Jack's right. We need to take the site variability into account, but the equations we have are good enough for a starting point. The critical aspect here is settlement prediction. Let's break it down. The Poisson ratio is generally between 0.2 to 0.5 for most of sites, but even for the small changes in Poisson ratio can lead to a large difference in settlement. What do you think, Lily? If the Poisson ratio increases, settlement increases. It affects the lateral strain of the soil. If the Poisson ratio increases, settlement increases. It affects the lateral strain of the soil. But I think the real issue is the relationship between the elastic modulus and shear modulus. And since the G is derived from ES, an error in estimating ES could lead to a significant settlement miscalculations. Everyone, I got the latest soil data from the site. The elastic modulus is much lower than we expected. We were initially assuming a value of 150 MPa, but the actual measurement is only 75 MPa. That's a huge difference, but it directly impacts the shear modulus. See, that's what I'm saying. The soil is not behaving the way we anticipated. We got to recalibrate our models. The equations we are working with, UV equal to Q into 1 minus mu by 4 into GR. 1 minus mu. If mu increases, settlement increases. Shows that the settlement depends heavily on G. It shows that settlement is heavily depending on G, which is derived from ES. ES is half of what we thought. If the ES is half of what we thought, G will also drop significantly. If ES is half of what we thought, then G will also automatically significantly, it will drop, leading to a much higher settlement. If G goes down, settlement goes up because it's inversely proportional. And if ES goes down, and G also goes down because ES and G are directly proportional. That means our Mudmat needs to be even bigger than we planned. To avoid a larger Mudmat settlement, that means we need to have a bigger Mudmat, even bigger Mudmat than we planned. This is a serious complication, but equations fundamental assumptions hold. If we use the correct value of ES, we can estimate G accurately and adjust our Mudmat design. However, we also have to make sure the equivalent circular footing radius is correct. Wait, I have been thinking, what if we scale the Mudmat area to compensate for the lower shear modulus? If we increase the Mudmat area, the equivalent radius will increase as well. If we increase the Mudmat area, equivalent radius also will increase as well. We can balance the settlement by spreading the load more evenly across a larger area. That means we are going to balance the settlement by spreading the load by more evenly to a larger area. This might mitigate the increased settlement from the soil's lower stiffness. Because the soil has lower stiffness, we need to compensate in the area. By increasing the area, we can distribute the load more evenly across a larger area. That this will mitigate the increased settlement because of soil's lower stiffness. That's a good idea. By increasing the area, we reduce the pressure on the soil. What would happen if we increase the area? It would reduce the pressure on the soil. That means radius is also increases, which lowers the settlement. If radius is increases and the low settlement is getting down, but we still need to be careful about the material cost. A bigger Mudmat cost means more materials. That means more construction time also. If we go too big, the cost skyrockets. If we go too big, the cost skyrockets. We need to find a balance. Maybe we can optimize the Mudmat design with a larger radius, but still minimize excess material. We could look into reinforcing the edges for air stability without increasing the area too much. This is exactly the type of thinking we need. That's the type of thinking we need. We can't rely on just one solution. It's about optimizing the design, considering the cost, and adding or adjusting for site-specific factors. But Jack, I'd like you to look into more cost-effective way. to increase the footprint without oversizing it. Alright, also we will use the revised value for years and calculate the G again and adjust the radius using the updated Mudmat, and I will recheck the settlement calculation. I'll make sure the soil data is correctly factored in. I will also check the site's variability again to make sure we are not overlooking anything. Excellent. That is why we are a great team. Jack, get started on the cost benefit analysis for the new design. Let's finalize those calculations. Alright, so time to put theory into practice. Sometimes the real world complexity of engineering forces us to think beyond the equations. Sometimes the real world complexity forces us to think beyond the equations, but with the right approach we can always find a solution. You have done an excellent work today. We are just getting started. This is going to be a greater design, and with the right adjustments the Mudmat will perform better than originally expected. Let's do this. This time we make sure the foundation holds. We got an offshore project with larger Mudmat foundation. The settlement calculation is crucial. Do you understand all the parameters? Do we all understand all the parameters? Yes. How do we account for that? But variability. What about the variability of soil? How do we account for that? We have to see like Mudmat area, upright, elastic shear modulus, all these are the inputs. But how do we account for the variability of the soil? How do we account for that? What about the variability of soil and how do we account for that? The soil variability is key, but let's focus on how we will handle the calculations. How do you think the shear modulus plays into this? You have to think like, how do you think the shear modulus plays into this? G is derived from ES and mu. But if the elastic modulus is off, doesn't that throw everything off? How precise do we need to be with the ES for this Mudmat to work? How precise do we need to be with the ES for this Mudmat to work? That's exactly the issue. That's exactly the issue. Small errors in ES could lead to large settlement differences. We need to be careful with assumptions. What's our next step? The soil report just came in. Actual elastic modulus not 150 like we expected. How much will this affect our calculations? That's a huge difference. What does this mean for the shear modulus? Can we still use the same formula? With ES is dropping, G will drop too. With ES dropping, G will drop too. The increase in settlement, doesn't it? This increases settlement, doesn't it? Should we be adjusting Mudmat size to compensate? The Mudmat's size to compensate? Yes, exactly. But how much? With the new G causes too much settlement for our design. Should we recalculate everything to find a workaround or find a workaround? Just looking at the board, if you use the formula with the lower G, the settlement increases, but increase the Mudmat area will also increase the cost or radius. How much should we increase? Should we increase the area? How much should we increase the area? Increasing the area sounds great, but will it be cost effective? Increasing the area sounds good, but will it be cost effective? That sounds great, but will it be cost effective? What if we go too big? Will it be the structurally viable or just wasteful? Thinking aloud, what's the optimal size? The formula shows larger radius decreases the settlement, but how much of increase in area will actually make the difference without overshooting cost? How much increase in the area will make a difference without overshooting the cost? Excellent points, all of you. What if we focused on a balance sizing Mudmat to reduce settlement without inflating cost too much? We should not inflate cost too much. Is there a middle ground? In practice, the soil varies across site. If you use average values of ES, and will it reflect the local conditions? How accurate are our models? That's the issue. Do we adjust the model to reflect the variability, or do we use a worst case scenario? How do we refine the settlement portion without data overload? Maybe we should model the extremes. If the Mudmat performs under the worst conditions, it's safer. But can we validate the actual site data? How do we balance safety and efficiency? We could slightly increase the Mudmat area by using the revised ES and G, and new radius will help with settlement. But are we still saying within the project budget? If you go larger, the foundation is more stable, but at what price? Is there a way to reinforce the edges rather than increase the area? Reinforcing the edges might work, but what about the material alternatives? Could we use different material to maintain the strength without increasing size? Perhaps we need to explore non-traditional materials. What's the performance trade-off between the cost, strength, size? Can we justify the choice? So we have increased the radius, adjust the settlement formula, reinforce edges, but how do we represent this to the client? Is this approach too conservative? I think the settlement will be within the acceptable limits, but is there a risk that the increased area might still cause soil instability?